Hi all, have a good day. I'm K. Surya, working as assistant professor in the Department of ECE at SNS College of Technology. So in this video, let us see about Kirchhoff's current law. Already we saw about Kirchhoff's voltage law. So there are two laws, Kirchhoff's current and voltage law. So these are very important in order to find out the current and voltages in a circuit. So we'll just refresh what is a node. So node is nothing but a point at which two or more elements are connected together. Next one is a path. So a path is nothing but a way where the elements are connected. So if no node was encountered more than once, then a set of nodes and elements that we have passed through is defined as a path. So if the node at which we started is the same as the node on which we end, then it is known as a loop. So when we start at one point and we rotate and we come to the same point, then that represents a loop. A branch is nothing but a single path in a network which is composed of one simple element and the node at each end of that element. Thus, a path is a particular collection of branches. So next we will see what is Kirchhoff's current law. So Gustav Robert Kirchhoff, a German university professor who was born at the time of Ohms, was doing his experimental work and he found out the Kirchhoff's current law, which in short is known as KCL. So Kirchhoff's current law states that the algebraic sum of the currents entering any node is equal to 0. Or else we can tell that the algebraic sum of the currents entering is equal to the algebraic sum of the currents leaving the node. So in general, we can tell a summation of n is equal to 1 to n, in is equal to 0. So this law represents a mathematical statement of the fact that charge cannot accumulate at a node. So node is not a circuit element, so it cannot store or generate or destroy any charge. So the currents must definitely become zero. So the three water pipes joined in a shape of a Y represents the hydraulic analogy. So this is a graphical representation of Kirchhoff's law. So in the diagram shown here, as you see, I1 enters the node, B enters the node, IC and ID leaves the node. So the sum of the current entering the node uh, is equal to sum of the current leaving the node. So these two currents IC and ID can be mentioned as minus IC and minus ID because it is leaving the node. So we can write as IA plus IB is equal to IC plus ID, or we can write it as IA plus IB minus IC minus ID is equal to 0. However, some of the currents leaving the node is also 0. So when you write in another way, you can write it as minus IA minus IB plus IC plus ID is equal to 0 as shown in this equation. So you can write in both the ways. So as I said earlier, IA plus IB is equal to IC plus ID. So sum of the currents going is in must equal the sum of the currents going out. So we will see an example here. So in this circuit, you find out the current through the resistor R3, which is mentioned as I here. If it is known that the voltage source supplies a current of 3 amps. So here, if you see, uh, you have a voltage source and a current source. So the current flowing in this resistance R1 is IR1. The current flowing through R2 is 2 amps. Current flowing through R3 we have to find, and this current is 5 amps. Okay, so here IR1 is equal to current flowing through R2 plus current flowing in this direction. So this current you can write it as, so since the total current at this particular node is IR1, you know that this current IR1 gets split into 2 at this junction. Okay, so we can write the current flowing here as IR1 minus 2 amps, right? So IR1 is sum of current flowing in this branch plus sum of current flowing in this branch. Since we know current flowing in this branch and the total current IR1, the current flowing in this branch can be written as IR1 minus 2 amps. And also the current, this 5 amps current will be entering at this junction into the circuit. So we can write I as both the currents are entering into this junction. So we can write I as IR1 minus 2 amps plus 5 amps. So from this we can find out I amps, IR1. So summing the currents flowing into the node, IR1 minus 2 minus I plus 5 is equal to 0. As I said you, IR1 minus 2 plus 5 is equal to I. Okay. So we know that the 10 volt source is supplying 3 amps current. So here IR1 is equal to 3 amps. So substituting IR1 is equal to 3 amps, we'll be getting I is equal to 3 minus 2 plus 5. So which will be equal to 6 amps. So the procedure here is, so we have to identify the goal of the problem, then we have to collect the known information, we have to design a plan, we have to construct an appropriate set of equations using the Kirchhoff's current law, and determine whatever additional information is required, and we have to work out the solution for it. So hope you understood Kirchhoff's current law. So let us take up some assessment questions. KCL deals with the conservation of, the options are momentum, mass, potential energy and charge. So as you know, KCL is nothing but Kirchhoff's current law. Current always deals with charge. So current is nothing but motion, charge in motion. So KCL deals with the conservation of charge. Next one is KCL is applied at, the options are loop, node, both loop and node, neither loop nor node. So we will be studying mesh analysis and nodal analysis. So KCL is nothing but it is applied to node. So your definition is algebraic sum of the currents entering the node is equal to sum of the currents leaving the node. So node, it represents node. So KCL is applied only at nodes. Next one, KCL can be applied for, the options are planar networks, non-planar networks, both planar and non-planar networks, and either planar nor non-planar networks. So KCL can be applied for both planar and non-planar networks, whereas KVL can be applied only for planar networks. So that is the limitation of KVL. Thank you for watching this video.